Morning students. Today we'll continue again with unit number 3, topic number 7, canal irrigation system. So this is an important topic, so listen to it or look at it very carefully and try to understand it. So first is introduction to canal irrigation system. A direct irrigation scheme which makes use of a weir or a barrage. Weir or barrage, these terms we'll learn in our upcoming units, as well as a storage irrigation scheme which makes use of a storage dam or a storage reservoir, necessitates the construction of a network of canals which was explained earlier in our previous classes. The entire system of main canals, branch canals, distributaries and minors is to be designed properly for a certain realistic value of peak discharge that must pass through them, so as to provide sufficient irrigation water to the commanded areas. We already know what is the commanded area. These canals have to be aligned and excavated either in alluvial soils or non-alluvial soils. It all depends upon which they are called, alluvial canals or non-alluvial canals, which is explained below. First one, alluvial soils and alluvial canals. The soil which is formed by transportation and deposition of silt through the agency of water over a course of time is called the alluvial soil. Example, in the deltic region, a river carries heavy charge of silt, which gets deposited on the adjoining land as and when the river overtops its banks during flood season. The process of silt deposition may continue over long periods of time, resulting in the formation of a soil called alluvial soil. The soil which is so formed by the continuous deposition of silt from the water flowing through a given area is hence called the alluvial soil. Now the area of alluvial soil is even and is having a flat surface slope as seen in the picture given below. Hard foundations are generally not available in this kind of soil. In prehistoric periods, the entire Indo-Gangetic plain was perhaps a depression and was filled up with constant silt deposition dropped from the water flowing through this area, resulting in the formation of an alluvial soil region. In this picture, you can see alluvial canal. The rivers flowing through such alluvial areas have a tendency to shift their courses. The riverbed consists of sand of considerable thickness and is therefore permeable. Whenever an irrigation structure is to be constructed on such a river, special precautions and design methods are to be adopted. Most of our North Indian rivers which pass through alluvial soils do pose these problems. So the canals when excavated through such soils are called alluvial canals. Canal irrigation is generally preferred in such areas as compared to the storage irrigation. Alluvial soil is very fertile as it can absorb a fair percentage of rainfall and retain in the substratum, making it highly productive as water remains available within the root zone of crops. Next, non-alluvial soils. Mountainous regions may go on disintegrating over a period of time, resulting in the formation of a rocky plain area called non-alluvial area. It has an uneven topography and hard foundations are generally available. The rivers passing through such areas have no tendency to shift their courses and they do not pose much problems for designing irrigation structures on them. Canals passing through such areas are called non-alluvial canals. Major portion of Maharashtra state is non-alluvial. Storage irrigation is preferred to canal irrigation in this type of soil. Non-alluvial soils may be permeable or impermeable, but generally they are non-permeable. In exam, you may get to write the difference between alluvial canals and non-alluvial canals. So this is a picture of non-alluvial canal, which can be readily or easily seen everywhere compared to alluvial canal. Next, these are the important definitions related to canal irrigation design which we'll do in our next classes. But right now I'm giving you few definitions. There are more which I'll continue in our next class. As for now, we'll start. First one is Gross Common Area, GCA. So what is gross common area? It is the total area bounded within the irrigation boundary of a project which can be economically irrigated without considering the limitation of the quantity of available water. It includes the cultivable as well as the uncultivable area. For example, ponds, residential areas, roads, reserve forests, etc. are the uncultivable areas of the gross common area. Next, a given irrigation canal system lies in a dome. So what does a dome mean? The area between two drainage and can economically irrigate the dome. It is obviously uneconomical to use the irrigation system to irrigate across the two drainages. Thus, the boundaries of gross common of a canal system is fixed by the drainages on both sides of the main irrigation canal as shown. The gross common area evidently represents the geographical area of the dome. Next, culturable or cultivable common area, which is CCA. Cultivable area is the cultivable part of the gross common area and includes all land of GCA on which cultivation is possible. It will thus include pastures and fallow lands which can be made cultivable. Obviously does not include uncultivable part of the gross common like populated areas, ponds, roads, reserve forests, usher land, etc. At any given time, however, all the cultivable land may not be actually under cultivation. So therefore, sometimes the CCA is divided into two categories, that is, number 1, cultivated portion of CCA, and number 2, cultivable but not cultivated portion of CCA. In the absence of detailed data, CCA may be assumed to be equal to 80% of GCA. I repeat, in the absence of detailed data, CCA may be assumed to be equal to 80% of GCA. Next, intensity of irrigation. The entire cultivated portion of the cultivable common area, which is CCA, is not proposed to be irrigated at one time or in one season to avoid intensive irrigation of a particular area, which may cause harmful effects like waterlogging, salinity, and malaria, etc. Moreover, due to shortage of irrigation water, larger area of the command is usually covered with partial coverage of the fields of different sub-areas or pockets. Some land of a particular sub-area is thus either allowed to take rest or is shown with crops which do not require irrigation water. Fields left unirrigated in one season will be supplied water in the next season when some other fields will be left unirrigated. The fields are thus supplied water in rotation over different crop seasons, thereby irrigating only about 40 to 60% of the fields of various sub-areas over a season. The irrigation water is thus usually supplied extensively, covering a larger area. Such as extensive irrigation covering a larger portion of the cultivable common is preferred to the intensive irrigation of the smaller portion of the common to avoid general famine conditions over some area, which should be totally left unirrigated if the entire water is used in intensive irrigation of some other portion. Extensive irrigation also helps in avoiding harmful effects of over-irrigation like salinity and waterlogging, which we'll learn in our last unit, which is caused by intensive irrigation. Due to these reasons, only a small percentage of CCA is brought under irrigation over a given season. This percentage of CCA proposed to be irrigated in a given season is called the intensity of irrigation of that season or seasonal intensity of irrigation. For example, the sanctioned intensity of irrigation under Bhakra Canal system is only 27.6% for Kharif season and 34.4% for Rabi season. Sometimes the intensity of irrigation is worked out over the entire year when it is called the annual irrigation intensity or annual intensity of irrigation AII, which may be defined as the percentage of CCA which may be irrigated annually. AII is thus obtained by dividing the gross irrigated area, that is the total area irrigated once in the year, plus the area irrigated more than once in that year, by the CCA. The annual intensity of irrigation is the sum total of intensities of irrigation of all the seasons of the year. The annual intensity of irrigation for Bhakra Canal system is thus computed by adding the intensity of irrigation for Kharif season and that for the Rabi season, giving combined annual irrigation intensity of 27.6 plus 34.4, which is equal to 62%. The annual irrigation intensity is usually found to be in the range of 40 to 60%, but needs to be raised to the range of 100 to 180% by cultivating larger parts of CCA with more than one crop in a year and through improved management and economical utilization of the available irrigation water. From the perusal of column 7 of table 4 under the first chapter of introduction to the subject, it can be seen that in India, Uttar Pradesh and Punjab states have already exceeded this figure of A11 beyond 100% to 139.6% and 133.4% respectively, with Haryana 90.2% and West Bengal 73.3%. Following these two best irrigated states, other states are far behind to such an extent that the overall annual intensity of irrigation in the country is only 45.9%. So there is a table number 4 from the book from where I have taken this note. In that table, it is seen that Uttar Pradesh and Punjab have exceeded the figures of AII beyond 100%. So this is your assignment for lecture number 20. The question is, the gross commanded area for a distributary is 6,000 hectares, 80% of which is cultivable irrigable. The intensity of irrigation for Rabi season is 50% and that for Kharif season is 25%. If the average duty at the head of the distributary is 2,000 hectares per cubic for Rabi season and 900 hectares per cubic for Kharif season, find out the discharge required at the head of the distributary from average demand considerations. So the answer is Kharif is 1.33 cubic, Rabi is 1.20 cubic and discharge is 1.33 cubic. So you have to find out three factors. First, Kharif season, second, Rabi season, and third is discharge, total discharge. So I repeat the question again. The gross commanded area for a distributor is 6,000 hectares, of which 80% is cultivable irrigable. So the intensity of irrigation for Rabi season is 50%, Kharif season is 25%. So if the average duty of the head of the distributor is 2,000 hectares per cubic for Rabi season and 900 hectares per cubic for Kharif season, then we have to find out the discharge required at the head of the distributary from average demand considerations. So the last date of submission is already mentioned here. If you have any doubts, you can contact me, and also now we'll go through a video. So you need to go watch it. In the upcoming classes, I'll be giving you questions related to those videos only. At the same time, now you can give your attendance in the chat box. And that's all for this class. Thank you.
The All-American Canal Landing Project started approximately 6 miles west of Yuma, Arizona. Approximately 21 million cubic yards of earth would be excavated, and more than 2 million square yards of 4-inch thick concrete would be used in the lining of the 23-mile canal. Reach 1 started downstream of a mountain peak called Pilot Knob and ended at the first hydroelectric power station called Drop 1. The actual process of lining the canal required heavy and complex machinery, but at some turns, construction crews employed a traditional building process: pouring, paving, and finishing by hand. Another engineering marvel involved the tie-ins. In order to control the flow of water during construction of the canal, construction crews used sheet piles to divert the water to enable construction of the tie-ins.
Those were the challenges. How do we tie this new concrete canal back to the old drop structures without interrupting flow? And so there was some unique things done on sheet piling, doing half the canal at one time and driving the sheet piling, cutting it off, dewatering it, putting in the concrete lining, and then pulling the ends out, let water start flowing back through, and flipping it back over and doing the other side. And that was a very interesting thing to watch and to see, but we were able to do it because we had we had 6 or 7 of these situations that we had to do this, and had some difficulties, but we were able to work through those things, and we were able to get it done and not interrupt the water flow. And
both man and machine were challenged by the same desert conditions: heat, wind, sand. During the summer months, temperatures regularly hit triple digits. Construction work schedules were shifted to night when temperatures cooled. Chiller tanks provided cooled water for mixing concrete. It was necessary to place the lining in the relative cool of the night, when temperatures came down into the reasonable mid-80 degrees Fahrenheit. The All-American Canal Lining Project met the target date of water delivery without disruption of water to agriculture or residents. More than 100 years ago, visionary leaders and builders brought water and prosperity to the Imperial Valley. The All-American Canal Lining Project continues their vision for generations to come.